Hello everyone, welcome back to my channel, Predicting the Future. Today we're gonna talk about characteristic functions and we're gonna see how it's actually identical to Fourier transform, which means that we can transform a function from time space to frequency space and vice versa. And that also exists in probability in random variables. So as you guys can see, my presentation has changed. I have been studying using a Jupyter book instead of a notebook, and in the future, I probably will move all the assets or all the materials into Jupyter book and publish on the website. So for those who are interested, you can go to ptfuture.net for those resources. So let's begin. Characteristic function. So as you can see here, a characteristic function of a random variable is an integral of the e to the power itx in a complex number space, and it, uh, and that's basically the Fourier transformation. Um, when the mu has a probability density function, then this is actually transformation of probability density function in Fourier transform. So there's some properties of characteristic function, but before we go to there, I want to go through what I'm gonna cover in this video. First, we're gonna see that the characteristic function always exists. First of all, characteristic function always exists because the e function was bounded in complex in the complex space, so it's always integrable. So any random variables can have a characteristic function. Secondly, we'll see that we can convert for a given characteristic function, we can convert it back to the probability measure or the cumulative distribution function, CDF. And also we're gonna see that we can also convert the characteristic function back to the probability density function. So that's what we're going to talk about today. Before that, we're going to see some of the properties of the characteristic function. So phi 0 equal to 1, which is obvious. When x is to 0, e to the power itx is 0, and that is just 1. If you take minus t, then that's just conjugate of the characteristic function. And the modulus of the characteristic function is less than or equal to 1. That's why it's bounded. And also, characteristic function is uniformly continuous. So if you take the modulus of phi t plus h minus phi t, and that is bounded by a constant. By this function, and that goes to, this can be as small as it can when h is smaller and smaller. So therefore, phi function is uniformly continuous. And also, expected value of given the CF characteristic function of a random variable x is phi, then ax plus b has a characteristic function of e to the power itx times the phi at. Also, if x and y are x1 and x2 are independent, then with CF phi 1 and phi 2, then x1 plus x2 has CF of phi 1 times phi 2. And let's see an example of characteristic function. Let's see what's the characteristic function of the standard normal distribution. So by definition, the characteristic function of standard normal distribution is integral of e to the power itx times the density function of the standard normal. And if we move the e to the power x itx into the power e of x minus x minus x minus it power 2, this is actually the same, taking out the extra term out. So but the last integral is just a integral of the standard normal of mean it and standard deviation 1. So the last integral is 1, and what we left is the e to the power minus t squared divided by 2. So that's the standard normal distribution, the CF function of standard normal distribution. Now we talk about the first important theorem, which is the inversion theorem, which means that if we know a characteristic function, then we can find out the probability distribution or probability measure. When I say there's the same probability distribution or probability measure, it's because the interval, the open interval, forms a pi system, and this more depth of those mathematical analysis that can prove that the pi system, if a probability measure, if two probability measure equals on a pi system, then they actually equal. They are actually the same probability function. So, if we can prove that the CDF mu of, let's say, from minus infinity to some number a is equal another CDF of another distribution random variable, then these two random distributions is actually the same, and they have the same probability measure. So just briefly mentioning that here. So given the phi and mu is the probability measure, then we can recover the probability measure mu from the phi function from this limit. So the limit of taking the limit of this integral here. So that's what we want to prove. Well, also there's another term here. If a and b are if the point A and point B, if they have probability measure 0, then which means they have no mass on those points A and B, then the last term will be just 0. If they are not, then this limit will have to add another extra term when A and B has mass on this measure. So let's prove this one. So first of all, let's see the integral inside, which is so sorry guys, this is this Jupiter Noble. One of the things that I don't like is I cannot zoom in. I don't know how to zoom in here. Usually in the R notebook, I can just zoom in, make it larger so you guys can see it properly. So this is some of the feature that doesn't exist on Jupyter book. But here, you see my highlights here. So the integral term here is actually the same of integral of e to the minus I y from a to b. So because of that, this integrand here is bounded by b minus a. We take the modulus, which is less than or equal to the integral of the modulus of the integrand inside the inner integrand, and that is just 1, so that becomes b minus a. And also because we are integrating, so which means that the whole term, so integrand here, because it's bounded minus t and t, and the integrand here is also bounded, the whole term here, the integral here from minus t to t, is integrable. So by the Fourier theorem, we know that we can exchange the integral sign, which I mean we can exchange the integral, two integrals. Is that because this term here can be written by replacing the integral term here to an integral itself. So we have a double integral here, and So if we exchange this integral, put the integration from minus t to t inside, and another integral of with respect to probability measure to outside, then we comes to this form. And since, so this is e to the power minus it x minus a, and e to the power minus it x minus b is actually they are complex numbers, so they can be written as cosine plus I sine, and when it divided by it, we will see that the cosine t minus it is actually all function. So the real part of the complex function, complex number, is when integrate it becomes 0. What we left is only the sine, and that's why we got the sine tx minus a divided by t minus sine tx minus b divided by t. And if we define, so you see, so we have two integral here minus each other. So if we define a function, define this form as a function r, so it's a function r of parameter theta and t, where theta in here is just t times x minus a. So this is function r. If we do a change of variable and we let s to be t theta, then the r function can be written as 2 times the integral of sine x divided by s. And this function we've seen that in first year calculus in university. But I'm gonna review that at the end of the video. So the r function can be written as, and if we define this sine s divided by s integration as a function s from st, which is integral from 0 to t sine x divided by x dx, it can be proved that it can be calculated actually that this, when t goes to infinity, the integral of sine x divided by x has a value of pi divided by 2. And I won't be showing here, but I will put it at the end of this video. So let's just assume this is the result we already proved. So, and then if we replace the two integral as using function r, then inside this part becomes r x minus at minus r x minus bt, and that is actually based on what value we get for x minus a, it's actually 2 times, which is we already see here, which is actually 2 times the sine of x minus a times the function s. And this will converge to, when t goes to infinity, which will converge to 2 pi or pi or 0, depends on what x value is located. So since rt is bounded, so the function r is bounded because the integral of sine x divided by x, which converges to pi over t, and by the maximum minimum theorem in the real analysis, we know that this function is bounded, and it's bounded by the 2 times the sup of this sine function, s function. So because it's bounded, we can use the bounded the dominant convergence theorem. So the limit, we take the limit inside, and that becomes the integral. So we take the limit, the limit goes inside of the integral. So the r minus r will becomes 2 pi times 1 over 2 pi, which is 1, and that becomes only when x is between a and minus b, then that will becomes mu, taking measure mu on the interval, open interval ab. And also the other case is when x equal to a or x equal to b, then that becomes pi, and when pi times 1 over 2 pi, that becomes 1 over 2 on measure mu on the 2 points a and b, and the other term is just 0. So that gives our result of this equation here, equation 1, let's say. So that's the inversion theorem, which we see is that we can recover the probability measure from its characteristic function. Another thing we can easily see is a corollary is that if the measure of a point A is actually this form, which is also easy to see. I'll leave it here. It's just a pure calculation. Well, maybe let's go through that. So it's pretty much the same thing. So let's prove this one is equal to mu on A, measure on A. So the integrand here, e to the minus ita is just times the phi t. The phi t is just integral of eit d mu. So it becomes double integral, and the two e functions becomes 1. That becomes e to the it x minus a, because this is bounded. So because the integrand inside is bounded, so it's integrable. So we can by the Fourier theorem we can exchange the integral sign. The outside becomes inside, inside becomes outside. So we first integrate from minus t to t dt of this exponential function. But that's just so that's just this form, and the cosine terms will cancel out. What we left is only sine term, and I is also cancel out. The 2 is also cancel out because there's 2 sine function, the 2 times sine, 2 times the sine function. So what we left is this one. And that is actually, we can split that into 2 sets. Integration of when x is not equal to a and x equal to a. When x equal to a, then the function, the integrand here is just 1. As you probably remember, sine x divided by x, when x go to 0, it's just 1. So when x equal to a, the integration is just becomes mu by measuring on the point A. But what about this term? This term, when t goes to infinity, because sine is bounded by 1, the denominator becomes larger and larger, so this becomes 0, and so the integral here becomes 0. So what we left here is just mu of the measure mu on the point A. So that's this corollary here. So the last theorem I want to talk about is, if we know the characteristic function, when can we recover the probability density function? Here it's very tricky. For those who don't know, not every random variable has a density function. Just be careful. In real world, that doesn't happen. But in the imaginary mathematical analysis world, the real pure world, that do happens. You can really find, you do find random variables that doesn't have probability density functions. But here, the theorem I'm gonna talk about here is when the characteristic function is integrable, which or I say converge absolutely, which means the integral of the phi absolute value of phi dt is finite, then we can recover its. Then we know that the probability measure mu do have a continuous density function, and that density function, we can recover that probability density function using this formula, which is 1 over 2 pi integral of e to the minus it x phi t dt. And this function f is bounded and it's continuous. So let's prove that. First, let's prove it's bounded. It's easy. Take the absolute value of f, which is less than or equal to the integral of absolute value of the integrand, and because of by the assumption we know this is finite, so it's bounded. Continuous. So we want to prove continuous. Then let's give any sequence xn and convert that sequence converges to some value x. We want to prove that fxn converges to fx. So because of that, let's say xn converges to x. If we define the function g to be where this is the integral to be e to the power it xn times phi t, and the function so that's function gn, and the function g to be e to the power minus itx phi t. So because those two functions are all continuous, we know that gn converges to g pointwise, and the modulus of the gn function is bounded by the phi t, the function phi, and because phi is integrable by the assumption, and therefore all the conditions, all the dominated convergence theorems conditions met, and we know then we can just take the limit of integration of gn, and that will converge to the function, the integral of g, and that is exactly of fxn converge to fx. Now let's see the density function. Let's derive. This is the density function here. This is the formula for the density function. As we see in the inversion theorem, we already see that. So the modulus of the integrand of the inversion formula is bounded by b minus a, and because phi is also the function phi, the characteristic function is integrable. So we know that this is the inversion formula. Inversion formula we saw above. So this will become this is the formula. So this is less than or equal to the absolute value of the integrand. So this one becomes is less than or minus a. So we take out this maximum value divided by 2 pi and take the integral. Or sorry, I lost the modulus of the phi t here. So there should be a absolute value of phi t inside this integral, and that is less than infinity. So we know that. Because of that, we know that we can, if we take a and b as closer and closer to each other, which means that b minus a becomes smaller and smaller. This is a constant term, so this one will become smaller and smaller, which means that the measure mu has no mass points, because that if get a and b closer and closer to any mass point, it's always smaller and smaller, so there's no mass on any points, which means that it's pretty nice probability measure. It's not a discontinuous probability measure. So because of that, if we take the measure of on the open interval of x to x plus h, some distance h, then by the inversion theorem, that's the inversion formula, and inside that we just saw that in the inversion theorem we can change that to an integral, which is also seen here. We can change that into integral of e to the minus itx from x to x plus h, and here we also exchange the integral, outside integration to outside, inside integral goes to outside goes to inside, and what we left inside of this integral of x to the x plus h is the integral here, and this is exactly the probability density function we see here in the theorem. If we take the derivative of this mu with respect to h, then by the fundamental theorem of calculus, this is what we are looking for. So that's the proof of deriving the probability density function using phi. As you see, let's go back to the Fourier transform. As you see, this is the Fourier transform. First, we transform the characteristic function is transforming, or let's assume that mu has a probability density function. The mu dx will become the probability density function f dx, right? So it becomes e to the itx times the probability density function f and dx, and that's the normal way of defining random variable when you see in a undergraduate level of probability series. So that's the transforming the probability density function by timing that with e to the itx. And when we want to recover the probability density function, that's what we see from this one, is that we times the phi function or with the inverse, which is e to the minus itx, which is exactly the same of the Fourier transformation, right? So that's how it's related to the Fourier transformation. Yeah, so that's it. Before you go, remember we haven't proved the integral of sine x over x from 0 to t when t goes to infinity has a value of pi over 2, and I'll prove that no. Okay, so now let's come back to our unsolved problem. We want to find the value of integral of sine x over x from 0 to infinity, which is defined to be the limit of 0 to integral of 0 to t for t goes to infinity, and we want to find the value and to be pi over 2. So the first thing, let's observe that 1 over x can be actually written as the integral from 0 to infinity of e to the minus mu x dx. This is easy to verify. I won't go through that here. So our original problem will become a double integral problem. So that becomes double integral of sine x. The 1 over x becomes was replaced by this one, and that becomes sine x e to the minus mu x dx, d mu and dx. And if this is integrable, we'll see that it's integrable later. If this is integrable, then by the Fourier theorem, we can actually exchange the integral and the two integrals, the 0 to the t will goes inside, and 0 to infinity goes outside. And the condition of that is this is integrable. This has to be finite. And then we can interchange the integral. So is it finite? Let's see. So the integral of sine x over x from 0 to infinity, which is actually less than or equal to the absolute value of the inner function here, and for this This is actually, let's look at this this sine absolute value of sine x over x. It is actually sine x over x is less than or equal to x. The absolute value of sine over x is less than or equal to x. The reason is simple. Remember the sine x. Sine x, x is actually the arc here, right? So x is here, and sine x is this line here, is the y here. So y is always less than or equal to the radius here, where the radius 1 here, the arc here is x. So we know that sine x over x, sine x is less than or equal to x, so absolute value of sine x divided x is less than or equal to 1. So this function here is less than or equal to integral from 0 to t dx, and that is less than, or this is equal to t, and which is finite. So that's the condition we need for forbidden zero, which means that we can exchange the signs, exchange the integrals here. Now we come to why we exchange sign, because now we will see that the inner integral here can be calculated easily. Well, no, not very easily, but it can be calculated. So now we go back. So this is the inner integral here. I want to find the value of this integral. So here we are integrating from 0 to infinity, from 0 to t sine x e to the minus mu x dx. And here we're going to use the partial integral, integration by parts. So here we are taking f, so f times g minus what f is so this is actually a derivative of some function, and another function g is sine x. So this derivative is actually equal to the derivative of function f, which is minus e to the power mu x over mu. If you take the derivative of f, that becomes what we have here, e to the minus mu x, and the function g is sine x. G prime is cosine x. So we use the integration by parts, and the minus, there's minus and plus, two minus, that becomes plus. That will becomes the function f times derivative of g, and this is what we have here. And this one is just when we take the t minus take the value of 0, sine x of sine of 0 is 0. So what we left for this term is just when we take the x equal to t. And then in this integral, we do another integration by parts. And this time what we are looking here is with f becomes f1 and g becomes g1, another function, different function. F1 is actually minus e to the minus mu x divided by mu squared. If you take derivative of f1, that becomes what we have here, e to the minus mu x divided by mu. And g1 is cosine x, so g1 derivative is minus sine x. We take into we apply the integration by parts again, and that becomes this part. So let's expand that. So this is taken down, and we take the value here. T becomes that when taking the value 0, it becomes 1 over mu squared. Minus minus becomes plus, and then this integral here becomes this one. So you see here, this is what we want to find out. This is the same term. So let's let this what we need to calculate to be s. Then we move around to move this part over to the other side of the equation. Well, first times mu squared. We cancel the denominator's part first. So here becomes mu squared s equals the other term. We move this over, so it becomes 1 plus mu squared s equals over here is we take out. So this becomes 1. Take out the e to the minus, the common term, e to the minus mu t, and then we have the rest of the term is mu sine t plus cosine t. So we have the integral of this term, which is s, this term, s, is actually equals to this value. So now we come back to our double integral question, which is this one, which is equal to what we need to find. And eventually we're going to take the limit of t to goes to infinity, but let's first take a finite when t is not infinity. So we'll take what we have just found on here, put it into this equation, and that gives us this one. So let's see. Right, so 1 over 1 plus mu square integral minus the other integral e to the power mu t divided by 1 over mu squared times this term here. So this one, let's call the equation formula of equation 4, and it is equation 5. And what we want to prove is the whole term equals to pi over 2. In fact, we're going to see this is pi over 2, and this term, when t goes to infinity, goes to 0. So this one, let's first find this one. This is easy. So what we need to do is take u to be equal to tangent x, and change the variables. The integral from 0 to infinity becomes taking integral of 0 to pi over 2, and that becomes 1 over tangent square x times the change of variable, derivative of tangent x times dx. But tangent derivative of tangent x is just 1 plus tangent x squared, so this two term cancelled. That becomes integral of 0 to pi over 2 dx, and that's pi over 2. So that's 4. And then we come back to 5. We want to prove the 5 when we take the limit when for t goes to infinity, the fifth equation goes to 0. So now we come back to 5. So this is 5. So we just did a little bit reorganizing. So this we expanded. So e to the minus mu t times mu sine t divided by 1 over mu squared, and we divide mu by both numerator and denominator. The denominator will become 1 over mu plus mu, and that has a minimum when mu equal to 1. So that's less than, and sum of t is less than or equal to 1. So the first term here will less than or equal to 2 times the integral of only the exponential term. Same here. The denominator 1 plus mu squared has a minimum at 1. So that's greater than or equal to 1. So this term will be less than or equal to also an integral of only the exponential term. And when t goes to infinity, the function e is actually becoming lower and lower, so it closer and closer to 0. So this one, the integral of this one and this one all goes to 0. So that means that the fifth term here, when t goes to 0, goes to infinity, goes to 0. And this one is just pi over 2. So that proves that our integral here, sine over x, from 0 to infinity is pi over 2. And that's it.